Consider this famous interview problem. You are given a text and a pattern, and you need to figure out if this pattern appears as a subsequence in this text. Most of you might already be familiar with the greedy algorithm involved in this problem. That is, you start traversing the text from left to right and you locate the first occurrence of the first character of the pattern. As soon as you get a match, you now start looking for the occurrence of the second character of the pattern, not in the entire string but on the suffix that you have remaining. If you repeat this algorithm for the remaining 4 characters, you will eventually be able to construct such a subsequence if it does exist. This algorithm is pretty simple to implement, but do you really understand why does this algorithm work? And can you modify it to solve problems on Codeforces and LeetCode? We will find out in this video. In fact, this algorithm is more powerful than you think. Let's look at some properties of this algorithm. Notice that it doesn't just give you a yes or no answer on whether a subsequence exists. It actually gives you that construction of that subsequence. Not only that, the construction that this algorithm produces has a very interesting property. If this is the text, you can notice that there can be several occurrence of pattern as a subsequence. For example, these green boxes, they match the pattern, but these blue boxes, they also match the pattern. However, if you list out all the possible such subsequences that match this pattern, you will notice that this algorithm always produces the lexicographically smallest sequence if the ordering is done on their indices. For example, this subsequence starts at index 8 and this subsequence starts at index 2. So naturally this is the lexicographically smallest such subsequence that is possible. Now let us look at a problem that deals with the lexicographical ordering of the values instead of the indices. You are given an array which contains integers from 1 to n. Now you need to find out the maximum length subsequence that only contains unique elements. But if there are more than one subsequence with maximal length containing only unique elements, then you need to figure out the lexicographically smallest such subsequence by the values of the elements. For example, in this array, this green subsequence has the maximal length that is possible, which is 4. But if you were to swap out this 3 with this 3, it would still have length as 4, but it would not be the lexicographically smallest because 1 is smaller than 3. So we should prioritize 1. So the problem is to find out the lexicographically smallest subsequence by values such that it has the maximal length and only contains unique elements. You can submit this problem in my Codeforces group. I will add a link in the comment section below. And a trivial variation of this problem also appeared in Codeforces round 967 as problem D, longest max min subsequence, which is a 1900 rated problem, but there is no prerequisite involved for solving this problem, and we will actually discuss this problem at the end of this video. And an easy version of this problem also appeared in LeetCode. First of all, let us figure out the maximum length of a subsequence that only contains unique elements. If you look at the indices of the elements, you will notice that there is a bijection between subsets and subsequences. Therefore, instead of finding subsequences, we can think about the maximum size of a subset that contains only distinct elements. And now the answer is obvious that it has to be equal to the number of unique elements in this array. Notice that how switching from subsequence to subset immediately led us to the answer. However, in some problems where DP is involved, if the problem asks you to compute some quantity over all the subsets, it is actually beneficial to use this bijection and think in terms of subsequence. Why? Because subsequence are ordered and DP lets you do operations on ordered elements. And in fact, we used this trick when we were solving the problem learning to paint from a recent Codeforces round. I also have a video editorial for this on my channel if you want to check it out. Before we discuss how to handle ties to ensure lexicographically smallest subsequence, let us go back to our original problem of subsequence matching and talk about the proof of correctness of the greedy algorithm that we had come up with. A common technique in competitive programming to prove the correctness of such greedy algorithms is known as exchange argument. And in this technique, you start with any optimal configuration that your algorithm might not produce. And then from that configuration, you perform a series of swaps and exchange elements one at a time, such that with every exchange, the answer does not get worse. That is, even though you are not able to improve the answer, you need to prove that the answer does not downgrades. Then after performing this series of swaps, if you can reach a configuration that your algorithm will also produce, then you can claim that your greedy algorithm is optimal. Let us look at how to apply the exchange argument in this problem. Notice that the final subsequence has to start at this, or this index. And suppose the optimal subsequence starts at this non-terminal element. Then you can say that if you swap out this element with the terminal element, the answer will not worsen. Why? Because this suffix is available to both the configuration, but in the new configuration, after swapping out this C for the terminal C, we have more possibility of subsequence matching because there are more number of elements than before. So what we are essentially doing is we are maximizing our chances of success by ensuring that we have the longest suffix that is available for the remaining characters of the pattern. Therefore, you can see that this exchange argument works. You can always exchange the first element for the terminal element and your answer will not get worse. And that is why the greedy algorithm for this problem is correct. Although this is a simple proof, remember this exchange argument, will come back to it later in a while. Let's go back to the problem of finding the maximum length subsequence with only unique elements. How do you also ensure that it is the lexicographically smallest subsequence? You might be tempted to start your subsequence from the smallest element, but this is obviously incorrect because you should focus on maximizing goal 1 even if it comes at the expense of goal 2. Therefore, we need to approach this problem in a different way. But how do you develop the intuition to think of alternate ways for this problem? A general tip here is to start small. That is, instead of worrying about all the elements of the subsequence that we are going to construct, let us only focus on the first element of that subsequence. What are the possible candidates for the first element of the subsequence? You can notice that if this is the possible candidate for the first element of the subsequence, at least one copy of all the unique elements should be on the right hand side of this element because we need to achieve goal 1 as well. So let us mark all such candidates in green. You will notice that this will be a prefix of this array. But let us focus on this element. Why did it not be a possible candidate for the first element? What exactly happened over here that all these boxes are green but this is not green? This is not a possible candidate because if you were to start a subsequence over here, there is no way that you will be able to accommodate 2 in your subsequence. Why? Because all the copies of 2 are behind us. Because if you start your subsequence over here, you will never ever be able to take 2 in your subsequence. So now this gives you a hint that whenever an element appears for the last time at any index, something interesting happens. What exactly, we are not sure yet, but definitely some strange thing happens when an element appears at an index for the last time. So let us go ahead and mark all such indices where an element appears for the last time in red. So you can see that there were 4 unique elements, there were 5 unique elements. So we marked the last occurrence of all these unique elements in red. Now it is easy to see that the final length of the subsequence will be equal to the number of red boxes, which will be equal to the number of unique elements in that array. But we still need to explore what is special about these red boxes and what exactly happens at each of these red boxes. In this image, all the red boxes indicate the last occurrence of the unique elements of the array. And all these green boxes, including the first red box, indicate the possible candidates for the first element of the final subsequence. As we discussed in the previous slide, 4 will never be a possible candidate for the first element if you haven't yet taken any 2 in your subsequence, because if you start your subsequence at element 4, you will never be able to accommodate 2 in your answer because the last occurrence is behind us. This means that your possible set of candidates for the first element are frozen in time unless you construct some part of your subsequence which will unlock 4 and the future elements. Now notice that if this is the last occurrence of 2 and we need to do something with 2 to unlock this 4, does this mean that we need to start the subsequence at 2? That is not true, because this last occurrence is safe over here. It means that you can do anything that you want with this prefix and you will never lose one copy of 2. So it is in your best interest to compute the best possible subsequence from this prefix, including this red element. Naturally, you would like to start your subsequence with element 1, and that is why it is colored blue. Blue represents that this element was taken in your final subsequence. But as soon as you take element 1, notice that you can never take elements to the left because a subsequence will only contain indices in increasing order. So all the elements to the left will become invalid. So since it is invalid, I have colored it with gray. But if this 2 is colored gray, all its copies should also be colored gray. Now that you have taken 1 in your answer, recall that the list of candidates is still frozen in the prefix because 4 will never be unlocked unless you take 2 in your answer. So what is the next thing that you could do? You can see that the next thing is to take 2 in your answer. So as soon as you take 2, you invalidate all the elements to the left and then you invalidate all the copies of 2 by marking it in gray. Now notice that 3 was also a possible candidate. So should we take 3 in our answer before unlocking 4 or should we wait some more? You can see that it is optimal to wait some more before taking this element in your answer, because there is a possibility that some more better elements gets unlocked. So as soon as you took 2 in your answer, you can see that 4 can now be a possible candidates for the current position. But 5 can never be a possible candidate because the last copy of 4 is behind us. So from this set of candidates, you need to do something and you need to take 4 in your answer as optimally as you can. And now you can see that it is optimal to take this copy of 3 in your answer and invalidate this copy, and then take this copy of 4 and you turn it blue. After you have taken this copy of 4, 5 will get unlocked. Why? Because all the previous unique elements that had their last occurrence in this prefix have already been taken. So you take this copy of 5, you color it blue, and then you invalidate all the other elements. So this gives us a pretty simple algorithm whose time complexity might be O of n square, but it is very simple to understand and implement. This is a summary of the algorithm. First, you mark all the last occurrence of each element in red. Then you collect the possible candidates for your first element, which will be a prefix of that array, and you need to stop collecting when you reach the first red index. And we know that you cannot move past a red index unless you have taken one copy of this element in your answer. Therefore, you will greedily construct the subsequence from the possible candidates that you have. And from exchange argument, you can see that if you have 2 copies of the candidate at this position and this position, you should always prioritize the leftmost copy because it maximizes your chances of success in future by leaving a longer suffix for the remaining characters to match. And then once you take an element, of course all the candidates to its left will be invalidated and you mark it with gray, and all the feature occurrence will also be invalidated. And then after you are constructed the best possible subsequence from the candidate, as soon as you take the candidate with the same value as the red colored box, you need to stop instead of constructing the entire subsequence right there. Why do you need to stop? Because some more interesting candidates might get unlocked after you have moved past the first red index. And then once you move past the red index, some more candidates will get unlocked. So you repeat this process again and again till you reach the end of the string. The time complexity of the algorithm that we have discussed so far is O of n square. How do we optimize the time complexity to O of n log n using some existing data structures and algorithms? Let us look at each component of the algorithm. How do we figure out these red boxes? That is the last occurrence of each of the unique values. To do that, you can simply iterate this array from right to left, and then you can keep track of the first time an element is seen in the reverse iteration. Then how do you maintain the prefix candidates? Because you will always want to know the minimum candidate that is possible. So since you want to query the minimum of a data structure every time, you can store these candidates in a set. Then how do you invalidate the left neighbors when you take an element? To do that, you can do that lazily, and by that I mean you just track the last blue box, you just track the index of the last blue box that you have taken, and if you encounter any element, just check if its index is less than this blue box or not. If it is, then it means that the element has already been invalidated. Then how do you apply the exchange argument here? And remember that exchange argument says that if there are 2 copies of an element, you should always prefer the leftmost copy. So how do you find the leftmost copy? To do that, let us maintain the indices of all the unique elements that we have seen so far. Notice that these indices would be sorted because we are iterating this array from left to right. Then you can use the upper bound function, which is essentially binary searching on this indices list, to locate the first occurrence of that candidate after the last blue box. Then how do you invalidate all the feature copies and all the future checkpoints? So for example, if you have taken this 2 over here, or if you have taken this 1 over here, if this was a red box, it will no longer be a red box. So how do you invalidate it? To do that, you can simply keep track of which elements have you already taken in your blue boxes in a set. Then as soon as you reach a red element, you can just check if the element has already been taken in your set. If it has been taken, then that red box means nothing. And then finally, it might look like that by the end of the operation, the candidate list might be non-empty and you might have to manually clear it out yourself. But this is a trick question. If you think about it, it will not be non-empty. It will actually be empty. Why? Because every element, one copy of every unique element will be taken by the time you reach its corresponding red box. So you don't even need to clear the set manually. It is in a way already cleared. This is the code for this problem. First of all, you figure out the location of all the red boxes. Then you start adding all the elements in the prefix one by one as a possible candidate, while also tracking the indices of all the possible candidates. Then if you hit a red element, you know that you cannot add any more candidates until you have taken one copy of that red element in your answer. Therefore, you greedily construct the partial subsequence such that the last element will be the one copy of the red element. And how do you greedily construct that subsequence? You always query for the minimum candidate, see if it has been invalidated by checking if it is to the left of the last blue box. Then once you get the candidate by exchange argument, you need to use the leftmost occurrence of the candidate that has not been invalidated. And that is why you can use the upper bound function to query for the first green box to the right of the last blue box. And once you get that location, you invalidate all the elements to the left of it by updating the current index, and then you take that element in your set until you reach one copy of the red box. And as soon as you reach one copy of the red box, you do not need to construct this subsequence anymore. You can delay the process because some good candidates might get unlocked in future. And as you can see, the time complexity is O of n log n. You can submit this problem in the Codeforces group. If you think about it, the strategy of starting with an initial set of candidates, then doing some operations to unlock new candidates is not something that is entirely new. In fact, this same strategy is used to perform topological sorting. You will remember that we start with the list of all the vertices with in degree 0 as unlocked vertices, and then we try to delete one unlocked vertex at a time, and if the in degree of a new node has become 0, we mark it as unlocked and we add it into the queue. So this is the same thing that is happening in this problem, and I hope you can see the correlation between them. If you want to solve some more problem on this concept of unlocking new candidates, you can try this problem called minimal labels on Codeforces, which has both this concept, the unlocking and the lexicographical ordering. But this problem has a unique twist, which is easy to miss if you are attempting it for the first time. So let me know your approach for this problem in the comment section below. You can also solve this problem using a segment tree. Notice that we are interested in the leftmost minimum candidate in this prefix. So if you have a segment tree that gives you the minimum of a subarray as well as the leftmost occurrence of that minimum, then you are done. You can query the segment tree. Suppose this is the minimum. You will take this element in your answer and then you need to invalidate all its future copies. How do you do that? You can simply go to those copies and set it to infinity so that it will never be returned as a minima. And then you shrink this prefix over here and you only query for the next candidate in this prefix. This is pretty easy to implement if you do have a segment tree that gives you the leftmost minima. But what if you do not have a segment tree that gives you the leftmost minima and you just have a normal segment tree that only gives you the minimum element of a range and nothing else? Would you still be able to solve this problem? It might seem challenging because for exchange argument you also need the leftmost minima. But that is easy to keep track of if you maintain the list of all the indices of all the candidates in a Deque, so that every time you take an element you invalidate all the older elements, and once you do the invalidation for every candidate, the front element of the queue will be the valid element and it will in fact be the leftmost possible candidate. The code for the segment tree solution turns out to be pretty simple and short if you rely on the @coder library's segment tree as a black box. I also have a video on my channel where I talk about how to use this @coder library to solve Codeforces problems. First, we store all the possible indices in a Deque and we locate all the red indices. Then we go through all the red indices and query the minimum in the valid segment. And as soon as we get the minima, we invalidate all the future copies by marking it as infinity. And then once you get the blue box, suppose it is here, you invalidate all the leftmost elements so that the front element of the Deque, which stores the indices, will always represent the leftmost minima that is possible. And we repeat this for all the red indices. Now, would you be surprised if I told you that this problem has a very simple O of n solution using monotonic stacks, and it is in fact connected to the problem of finding the next greater element, which you might have already solved in the past. Take a minute to pause this video and think about how you would incorporate monotonic stacks to solve this problem in O of n. Okay, let's look at the solution. If you have this array and suppose this is the first red box. So far we have been saying that all of these elements are possible candidates for the first element. But let's be realistic here. Are all of these elements equally likely to be the first element? No, because when we had seen the first element 3, we called it as a probable candidate. But as soon as 2 arrived, can 3 ever be a candidate? No, because when given the choice between 3 and 2, you will always pick 2 and this 3 will always get invalidated. So why are we even keeping it in the list of possible candidates even? Let's be realistic and let's remove it altogether. Then once you encounter this element, which is 1, can this element ever be a realistic candidate? Not at all, because whenever given the choice, you will always select this element. So let us invalidate this element before we even reach the red box. Then we arrive at 4. Can 4 ever be a candidate? Yes, it can be, because it has a smaller element to the left and once this candidate goes out in the final answer, 4 will have the opportunity to shine and it will become the new minimum element of this valid segment. So now you kind of see what is happening, right? For every element, the next realistic candidate is the next greater element to its right. So even before arriving at the red box, we can keep on trimming the candidates and we will only have the realistic candidates in a stack. But suppose you have 1 and 4 in a stack and then you arrive at this red box. Now you know that you cannot go forward until you take one copy of the red element. However, notice that the stack now contains only the realistic candidates. Therefore, you just need to locate where 4 is in the stack and then you need to take all of these elements in your answer. However, the only challenge is that you cannot remove elements from the bottom of the stack. So how do you deal with that problem and how do you efficiently find 4 in the stack? Of course, you might think of fancy ways of using a Deque as a stack so that you can pop from both the ends, and that is correct, but I'll show you a very elegant way to achieve this same process using a simple stack only. From exchange argument, you already know that the stack will contain at most one copy of each element because we are only storing the realistic candidates. Then when you arrive at a red index, you know that you cannot move on to the next element before taking one copy of this element. And suppose that copy is buried deep in the stack, suppose it is here. Notice that you cannot take this element before taking these elements which are buried in the stack as well. Why? Because all of these elements have higher priority than this element. So you have to go through these set of elements to arrive over here. Why? Because all of these are realistic candidates. And this node will get opportunity to be the element of the final subsequence after these nodes have cleared out. So instead of popping the bottom of the stack and then storing the answer somewhere, we can instead maintain the location of the locked index. That is, we can say that this red box is now locked in the stack, and if it is locked in the stack, then we can say that no one can pop it from the stack, no matter if it is infinity or minus infinity. No element can ever pop it from the stack, and this is the variation from the next greater element, because in the next greater element problem, any new element that arrives, if it is the smallest one, it can pop everything. But now you have to compulsorily lock this element because it has now been taken in your answer. So you lock this element and then you keep on adding new candidates. So for the new candidates, you follow the same process of finding the next greater element, but you ensure that you never pop more than this red box over here. And notice that the final stack is your answer. The final stack will contain all the candidates in the correct order. So pretty cool, right? Like you just maintain the possible candidates, you just maintain the realistic candidates, and at the end, whatever stack that remained is your answer. Here is a simple implementation of the stack based idea. You iterate through the list of candidates in the prefix, and if that candidate is not present inside the stack, you add it on the stack. But just like we do in the next greater element problem, we will remove all the candidates from the top of the stacks that have become unrealistic. But we need to make sure that we never pop further than the locked index that we have over here. And then we remove those elements from the stack and we push this element on top of the stack. Finally, if this element is really a red element, then we need to lock the stack at the position where this element appears. So we simply maintain a variable denoting the position of the locked index in the stack. And just like that, in 5 to 6 lines of code using stack, you can solve this problem in O of n. Here is the problem statement of the 1900 rated Codeforces problem that we discussed at the start of the video. In this variation of the problem, instead of finding out the lexicographically smallest such subsequence, you need to alternate between smallest and largest choice of the positions that you are currently on. But this variation is pretty simple, and you can in fact use our old code and modify it by adding 4 to 5 lines of new code to make it work for this problem. Pause this video and try to see if you can come up with the solution yourself. This is the code for this problem. Notice that the only difference in this version is that from this list of candidates, you sometimes have to query the minimum and sometimes have to query the maximum. But luckily for us, we have stored all of these candidates in a set, and set provides easy access to minima as well as maxima. Therefore, this is my same code as before with just 3 to 4 lines added to make it work for this problem. So we just need to track whether we need to take a minima or a maxima. And then every time we are selecting candidates, if we need to take a maxima, we take the maxima, else we take the minima. And after we have taken one element, we flip the choice. And that is it. The rest of the code is exactly the same as before. We discussed multiple approaches to this problem that really demonstrates the power of data structures and algorithms. In fact, this problem can even be solved with heaps as well as lazy segment tree. You can take a look at the editorial for the heaps solution and the comments section for the lazy segment tree solution. If you think that the connection to stacks and the next greater element was far-fetched, then it probably means that you are not well versed with the concept of monotonic stacks. To improve your grasp on monotonic stacks, you can watch these 2 videos on my channel that deal with monotonic stacks. However, even with multiple approach to this problem, you will notice that one common link between them was the concept of red indexes, which is the last occurrence of any element, and the exchange argument, which says that you should always prioritize taking the leftmost possible available element. You can find the code, slides, and the link to the contest where you can submit all the versions of the problems discussed in this video in the pinned YouTube comments. If you need some clarification or help, feel free to reach out to me on my Discord server or on the Codeforces blog that I will create for this video. All the code for this video will also be available on cfstep.com.